Section 22 of All About Coffee. This is a Librivox recording. All Librivox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Read by Paul Lawley-Jones. All About Coffee by William Ukers. Chapter 27, The Chemistry of the Coffee Bean, by Charles W. Trigg, Industrial Fellow of the Mellon Institute of Industrial Research, Pittsburgh, 1916 to 1920. Part 2. The Chemistry of Roasting. The effect of the heat in the roasting of coffee is largely evidenced as a destructive distillation and also as a partial dehydration. At the same time, oxidizing and reducing reactions probably occur within the bean, as well as some polymerization and interreactions. A loss of water is to be expected as the natural outcome of the application of heat, and analyses show that the moisture content of raw coffee varies from 8 to 14%, while after roasting it rarely exceeds 3% and frequently falls as low as 0.5%. The loss of the original water content of the green bean is not the only moisture loss. For many of the constituents of coffee, notably the carbohydrates, are decomposed upon heating to give off water, so that analysis before and after roasting is no direct indication of the exact amount of water driven off in the process. If it be desired to ascertain this quantity accurately, catching of the products which are driven off and determination of their water content becomes necessary. The carbohydrates both dehydrate and decompose. The result of the dehydration is the formation of caramel and related products which comprise the principal coloring matters in coffee infusion. That portion of the carbohydrates known as pentosands gives rise to furforaldehyde, one of the important components of caffeol. The effect of roasting upon the fat content of the beans is to reduce its actual weight, but not to change appreciably the percentage present, since the decrease in quantity keeps pace fairly well with the shrinkage. Some of the more volatile fatty acids are driven off, and the fats break down to give a larger percentage of free fatty acids, some light esters, acrylane, and formic acid. If the roast be a very heavy one, or is brought up too rapidly, the fat will come to the surface through breaking of the fat cells, with a decided alteration in the chemical nature of the fat and with a pronounced expansion and cracking. Decomposition of the caffeine acid salt and considerable sublimation of the caffeine also occur. The majority of the caffeine undergoes this volatilization unchanged, but a portion of it is probably oxidized with the formation of ammonia, methylamine, dimethylparabenic acid, and carbon dioxide. This reaction partly explains why the amount of caffeine recovered from the roaster flues is not commensurate with the amount lost from the roasting coffee, although incomplete condensation is also an important factor. Microscopic examination of the roasted beans will show occasional small crystals of caffeine in the indentations on the surface where they have been deposited during the cooling process. The compound or compounds known as cafetenic acid are probably the source of catechol, as the proteins are of ammonia, amines, and pyrols. The crude fiber and other unnamed constituents of the raw beans react analogously to similar compounds in the destructive distillation of wood, giving rise to acetone, various fatty acids, carbon dioxide, and other uncondensable gases, and many compounds of unknown identity. During the course of roasting and subsequent cooling, these decomposition products probably interact and polymerize to form aromatic tar-like materials and other complexes which play an important role among the delicate flavors of coffee. In fact, it is not unlikely that these reactions continue throughout the storage time after roasting, and that upon them the deterioration of roasted coffee is largely dependent. Speculation upon what complex compounds are thus formed offers much attraction. A notable one by Sayer postulates the reaction between acrylane and ammonia to give methylpyridine, which in turn with furfural forms furfural vinyl pyridine. This, upon reduction, would produce the alkaloid conin, traces of which have been found in coffee. Although furfural is the natural decomposition product of pentasands, furfuryl alcohol is the main furane body of coffee aroma. This would indicate that active reducing conditions prevail within the bean during roasting, and the further fact that carbon monoxide is given off during roasting makes this seem quite probable. If one admits that cafetanic acid exists in the green bean, that upon oxidization it gives viridic acid, and that it is concentrated in the outer layers of the bean, as certain investigators have claimed, then there is chemical proof of the existence of oxidizing conditions about the exterior of the bean. In any event, however, the fact that oxidizing conditions predominate on the external portion of the bean is obvious. Accordingly, our meager knowledge of the chemistry of roasting indicates that while external layers of the roasting beans are subjected to oxidizing conditions, reducing ones exist in the interior. Further experimentation, no doubt, will prove this to be the case. Attempts have been made to retain in the beans the volatile products, which normally escape, both by coating previous to roasting and by conducting the process under pressure. However, the results so obtained were not practical, since the cup values were decreased in the majority of cases, and the physiological effects produced were undesirable. In cases where the quality was improved, the gain was not sufficient to recompense the roaster for the additional expense and difficulty of operation. Various persons have essayed to control the roasting process automatically, but the extreme variance in composition of different coffees, the effect of changing atmospheric conditions, and the lack of consistency in the calorific power of fuels have conspired to defeat the automatic roasting machine. It is even doubtful whether Di Mattia's process for roasting until the vapors evolved produce a violet color when passed into a solution of fuchsin decolorized with sulfur dioxide is commercially reliable. Many patents have been granted for the treatment of coffees immediately prior to or during roasting with the object of thus improving the product. The majority of these depend upon adding solutions of sugar, calcium saccharate, or other carbohydrates, and in the case of Eckhart, of small percentages of tannic acid and fat. In direct opposition to this latter practice, Jurgens and Westphal apply alkali, ostensibly to lessen the tannic acid content. Brugier sprays a solution containing caffeine upon the roasting berries, and Potter roasts the coffee together with chicory, effecting a separation at the end. The exact effect which roasting with sugars has upon the flavor is not well understood, but it is known that it causes the beans to absorb more moisture due to the hygroscopicity of the caramel formed. For instance, berries roasted with the addition of glucose syrup hold an additional 7% of water and give a darker infusion than normally roasted coffee. When the green coffee is glazed with cane sugar prior to roasting, the losses during the process are much higher than ordinarily, on account of the higher temperature required to attain the desired results. Losses for ordinary coffee taken to a 16% roast are 9.7% of the original fat and 21.1% of the original caffeine, while for sugar-glazed coffee, the losses were 18.3% of the original fat and 44.3% of the original caffeine, using 8 to 9% sugar with Java coffee. Grinding and packaging. It is a curious fact that green coffee improves upon aging, whereas after roasting it deteriorates with time. Even when packed in the best containers, age shows to a disadvantage on the roasted bean. This is due to a number of causes, among which are oxidation, volatilization of the aroma, absorption of moisture and consequent hydrolysis, and alteration in the character of the aromatic principles. Doolittle and Wright, in the course of some extensive experiments, found that roasted coffee showed a continual gain in weight throughout 60 weeks, this gain being mostly due to moisture absorption. An investigation by Gould also demonstrated that roasted coffee gives off carbon dioxide and carbon monoxide upon standing. The latter, apparently produced during roasting and retained by the cellular structure of the bean, diffuses therefrom, whereas the former comes from an anti-roasting decomposition of unstable compounds present. The surface of the whole bean forms a natural protection against atmospheric influences, and as soon as this is broken, deterioration sets in. On this account, coffee should be ground immediately before extraction if maximum efficiency is to be obtained. The cells of the beans tend to retain the fugacious aromatic principles to a certain extent, so that the more of these which are broken in grinding, the greater will be the initial loss and the more rapid the vitiation of the coffee. It might, therefore, seem desirable to grind coarsely in order to avoid this as much as possible. However, the coarser the grind, the slower and more incomplete will be the extraction. A patent has been granted for a grind which contains about 90% fine coffee and 10% coarse, the patentee's claim being that in his irregular grind, the coarse coffee retains enough of the volatile constituents to flavor the beverage, while the fine coffee gives a very high extraction, thus giving an efficient brew without sacrificing individuality. In packaging roasted coffee, the whole bean is naturally the best form to employ. But if the coffee is ground first, King found that deterioration is most rapid with the coarse ground coffee, the speed decreasing with the size of the ground particles. He explains this on the ground of ventilation. The finer the grind, the closer the particles packed together, the less the circulation of air through the mass, and the smaller the amount of aroma which is carried away. He also found that glass makes the best container for coffee, with the tin can and the foil-lined bag with an inner lining of glassine not greatly inferior. Considerable publicity has been given recently to the method of packing coffee in a sealed tin under reduced pressure. While thus packing in a partial vacuum undoubtedly retards oxidation and precludes escape of aroma from the original package, it would seem likely to hasten the initial volatilizing of the aroma. Also, it would appear from Gould's work that roasted coffee evolves carbon dioxide until a certain positive pressure is attained, regardless of the initial pressure in the container. Accordingly, vacuum packing apparently enhances the decomposition of certain constituents of coffee. Whether this result is beneficial or otherwise is not quite clear. Brewing. The old-time boiling method of making coffee has gone out of style because the average consumer is becoming aware of the fact that it does not give a drink of maximum efficiency. Boiling the ground coffee with water results in a large loss of aromatic principles by steam distillation, a partial hydrolysis of insoluble portions of the grounds, and a subsequent extraction of the products thus formed, which give a bitter flavor to the beverage. Also, the maintenance of a high temperature by the direct application of heat has a deleterious effect upon the substances in solution. This is also true in the case of the pumping percolator and any other device wherein the solution is caused to pass directly into steam at the point where heat is applied. Warm and cold water extract about the same amount of material from coffee, but with different rates of speed, an increase in temperature decreasing the time necessary to effect the desired result. It is a well-known fact that rewarming a coffee brew has an undesirable effect upon it. This is probably due to the precipitation of some of the water-soluble proteins when the solution cools, and their subsequent decomposition when heat is applied directly to them in reheating the solution. The absorption of air by the solution upon cooling, with attendant oxidation, which is accentuated by the application of heat in rewarming, must also be considered. It is likewise probable that when an extract of coffee cools upon standing, some of the aromatic principles separate out and are lost by volatilization. The method of extracting coffee which gives the most satisfaction is practiced by using a grind just coarse enough to retain the individualistic flavoring components, retaining the ground coffee in a fine cloth bag, as in the urn system, or on a filter paper, as in the trickolator, and pouring water at boiling temperature over the coffee. During the extraction, a top should be kept on the device to minimize volatilization, and the temperature of the extract should be maintained constant at about 200 degrees Fahrenheit after being made. Whether a repouring is necessary or not is dependent upon the speed with which the water passes through the coffee which in turn is controlled by the fineness of the grind and of the filtering medium. The water extract. Although many analyses of the whole coffee bean are available, but little work has been reported upon the aqueous extracts. The total water extract of roasted coffee varies from 20 to 31% in different kinds of coffee. The following analysis of the extract from a Santos coffee may be taken as a fair average example of the water-soluble material. Table 4. Analysis of Santos coffee extract, dry basis. Ether extract, fixed, 1.06%. Total nitrogen, 3.4%. Caffeine, 5.42%. Crude fiber, 0.25%. Total ash, 17.43%. Reducing sugar, 2.7%. Cafetanic acid, 15.33%. Protein, 7.71%. It is difficult to make the trade terms such as acidity, astringency, etc., used in describing a cup of coffee conform with the chemical meanings of the same terms. However, a fair explanation of the cause of some of these qualities can be made. Careful work by Warnier showed the actual acidities of some East India coffees to be Table 5. Acidity of some East India coffees. Coffee from Sinjai. Acid content 0.033%. Timor 0.028%. Bautane 0.019%. Bungay 0.016%. Luwai 0.021%. Wallow Pengenten 0.018%. Kawi Rejo 0.015%. Palman Chasem 0.022%. Malang 0.013%. These figures may be taken as reliable examples of the true acid content of coffee, and though they seem very low, it is not at all incomprehensible that the acids which they indicate produce the acidity in a cup of coffee. They probably are mainly volatile organic acids together with other acidic-natured products of roasting. We know that very small quantities of acids are readily detected in fruit juices and beer, and that variation in their percentage is quickly noticed, while the neutralization of this small amount of acidity leaves an insipid drink. Hence, it seems quite likely that this small acid content gives to the coffee brew its essential acidity. A few minor experiments on neutralization have proven that a very insipid beverage is produced by thus treating a coffee infusion. The body, or what might be called the licorice-like character, of coffee is due conceivably to the presence of bodies of a glucosidic nature and to caramel. Astringency, or bitterness, is dependent upon the decomposition products of crude fiber and chlorogenic acid, and upon the soluble mineral content of the bean. The degree to which a coffee is sweet-tasting or not is, of course, dependent upon its other characteristics, but probably varies with the reducing sugar content. Aside from the effects of these constituents upon cup quality, the influence of volatile aromatic and flavoring constituents is always evident in the cup valuation and introduces a controlling factor in the production of an individualistic drink. Coffee extracts. The uncertainty of the quality of coffee brews as made from day to day, the inconvenience to the housewife of conducting the extraction, and the inevitable trend of the human race toward labor-saving devices have combined their influences to produce a demand for a substance which will give a good cup of coffee when added to water. This gave rise to a number of concentrated liquid and solid extracts of coffee which, because of their general poor quality, soon brought this type of product into disrepute. This is not surprising, for these preparations were mainly mixtures of caramel and carelessly prepared extracts of chicory, roasted cereals, and cheap coffee. Liquid extracts of coffee galore have appeared on the market only soon to disappear. Difficulty is experienced in having them maintain their quality over a protracted period of time, primarily due to the hydrolyzing action of water on the dissolved substances. They also ferment readily, although a small percentage of preservative, such as benzoate of soda, will halt spoilage. So much trouble is not encountered with coffee extract powders, the so-called soluble or instant coffees. The majority of these powdered dry extracts do, however, show great affinity for atmospheric moisture. Their hygroscopicity necessitates packing and keeping them in airtight containers to prevent them running into a solid, slowly soluble mass. The general method of procedure employed in the preparation of these powders is to extract ground roasted coffee with water and to evaporate the aqueous solution to dryness with great care. The major difficulty which seems to arise is that the heat needed to effect evaporation changes the character of the soluble material, at the same time driving off some volatile constituents which are essential to a natural flavor. Many complex and clever processes have been developed for avoiding these difficulties, and quite a number of patents on processes and several on the resultant product have been allowed. But the commercial production of a soluble coffee of freshly brewed coffee duplicating powder is yet to be accomplished. However, there are now on the market several coffee extract powders which dissolve readily in water, giving quite a fair approximation of freshly brewed coffee. The improvement shown since they first appeared augurs well for the eventual attainment of their ultimate goal. Adulterants and substitutes. There would appear to be three reasons why substitutes for coffee are sought: the high cost or absence of the real product, the acquiring of a preferential taste by the consumer for the substitute, and the injurious effects of coffee when used to excess. Makers of coffee substitutes usually emphasize the latter reason, but many substitutes which are, or have been, on the market seem to depend for their existence on the other two. Properly speaking, there are scarcely any real substitutes for coffee. The substances used to replace it are mostly like it only in appearance and barely simulate it in taste. Besides, many of them are not used alone, but are mixed with real coffee as adulterants. The two main coffee substitutes are chicory and cereals. Chicory, succory, Cicorium intybus, is a perennial plant growing to a height of about 3 feet, bearing blue flowers, having a long tap root, and possessing a foliage which is sometimes used as cattle food. The plant is cultivated generally for the sake of its root, which is cut into slices, kiln-dried, and then roasted in the same manner as coffee, usually with the addition of a small proportion of some kind of fat. The preparation and use of roasted chicory originated in Holland about 1750. Fresh chicory contains about 77% water, 7.5 gummy matter, 1.1 of glucose, 4 of bitter extractive, 0.6 fat, 9.0 cellulose, inulin and fiber, and 0.8 ash. Pure roasted chicory contains 74.2% water-soluble material comprised of 16.3% water, 26.1 glucose, 9.6 dextrin and inulin, 3.2 protein, 16.4 coloring matter, and 2.6 ash, and 25.8% insoluble substances, namely 3.2% protein, 5.7 fat, 12.3 cellulose, and 4.6 ash. The effect of roasting upon chicory is to drive off a large percentage of water, increasing the reducing sugars, changing a large proportion of the bitter extractive and inulin, and forming dextrin and caramel, as well as the characteristic chicory flavor. The cereal substitutes contain almost every type of grain, mainly wheat, rye, oats, buckwheat, and bran. They are prepared in two general ways: by roasting the grains or the mixtures of grains with or without the addition of such substances as sugar, molasses, tannin, citric acid, etc., or by first making the floured grains into a dough and then baking, grinding, and roasting. Prior to these treatments, the grains may be subjected to a variety of other treatments, such as impregnation with various compounds or germination. The effect of roasting on these grains and other substitutes is the production of a destructive distillation, as in the case of coffee, the crude fiber, starches, and other carbohydrates, etc., being decomposed with the production of a flavor and an aroma faintly suggesting coffee. The number of other substitutes and imitations which have been employed are too numerous to warrant their complete description, but it will prove interesting to enumerate a few of the more important ones, such as malt, starch, acorns, soya, beans, beetroots, figs, prunes, date stones, ivory nuts, sweet potatoes, beets, carrots, peas, and other vegetables, bananas, dried pears, grape seeds, dandelion roots, rinds of citrus fruits, lupine seeds, whey, peanuts, juniper berries, rice, the fruit of the wax palm, kola nuts, chickpeas, cassia seeds, and the seeds of any trees and plants indigenous to the country in which the substitute is produced. Aside from adulteration by mixing substitutes with ground coffee, and an occasional case of factitious molded berries, the main sophistications of coffee comprise coating and coloring the whole beans. Coloring of green and roasted coffees is practiced to conceal damaged and inferior beans. Lead and zinc chromates, Prussian blue, ferric oxide, coal tar colors, and other substances of a harmful nature have been employed for this purpose, being made to adhere to the beans with adhesives. As glazes and coatings, a variety of substances have been employed, such as butter, margarine, vegetable oils, paraffin, Vaseline, gums, dextrin, gelatin, resins, glue, milk, glycerin, salt, sodium bicarbonate, vinegar, Irish moss, isinglass, albumen, etc. It is usually claimed that coating is applied to retain aroma and to act as a clarifying agent, but the real reasons are usually to increase weight through absorption of water, to render low-grade coffees more attractive, to eliminate byproducts, and to assist in advertising. Methods of analysis of coffees: official and tentative. Sole responsibility for any errors in compilation or printing of these methods is assumed by the author. Green coffee. Number 1. Macroscopic examination, tentative. A macroscopic examination is usually sufficient to show the presence of excessive amounts of black and blighted coffee beans, coffee hulls, stones, and other foreign matter. These can be separated by hand-picking and determined gravimetrically. Number 2. Coloring matters, tentative. Shake vigorously 100 grams or more of the sample with cold water or 70% alcohol by volume. Strain through a coarse sieve and allow to settle. Identify soluble colors in the solution and insoluble pigments in the sediment. Roasted coffee. Number 3. Macroscopic examination, tentative. Artificial coffee beans are apparent from their exact regularity of form. Roasted legumes and lumps of chicory, when present in whole roasted coffee, can be picked out and identified microscopically. In the case of ground coffee, sprinkle some of the sample on cold water and stir lightly. Fragments of pure coffee, if not over-roasted, will float, while fragments of chicory, legumes, cereals, etc. will sink immediately, chicory coloring the water with a decided brown. In all cases, identify the particles that sink by microscopical examination. Number 4. Preparation of sample, official. Grind the sample to pass through a sieve having holes 0.5 mm in diameter and preserve in a tightly stoppered bottle. Number 5. Moisture, tentative. Dry 5 grams of the sample at 105 to 110 degrees centigrade for 5 hours and subsequent periods of an hour each until constant weight is obtained. The same procedure may be used, drying in vacuo, at the temperature of boiling water. In the case of whole coffee, grind rapidly to a coarse powder and weigh at once portions for the determination without sifting and without unnecessary exposure to the air. Number 6. Soluble solids. Tentative. Place 4 grams of the sample in a 200 cubic centimeter flask, add water to the mark, and allow the mass to infuse for 8 hours with occasional shaking. Let stand 16 hours longer without shaking, filter, evaporate 50 cubic centimeters of filtrate to dryness in a flat-bottomed dish, dry at 100 degrees centigrade, cool, and weigh. Number 7. Ash. Official. Chart a quantity of the substance, representing about 2 grams of the dry material, and burn it until free of carbon at a low heat, not to exceed dull redness. If a carbon-free ash cannot be obtained in this manner, exhaust the charred mass with hot water, collect the insoluble residue on a filter, burn till the ash is white or nearly so, and then add the filtrate to the ash and evaporate to dryness. Heat to low redness until ash is white or greyish-white, and weigh. Number 8. Ash insoluble in acid. Official. Boil the water-insoluble residue obtained as directed under 9, or the total ash obtained as directed under 7, with 25 cubic centimeters of 10% hydrochloric acid, specific gravity 1.050, for 5 minutes. Collect the insoluble matter on a Gooch crucible or an ashless filter, wash with hot water, ignite, and weigh. Number 9. Soluble and insoluble ash. Official. Heat 5 to 10 grams of the sample in a platinum dish of from 50 to 100 cubic centimeters capacity at 100 degrees centigrade until the water is expelled, and add a few drops of pure olive oil and heat slowly over a flame until swelling ceases. Then place the dish in a muffle and heat at low redness until a white ash is obtained. Add water to the ash in the platinum dish, heat nearly to boiling, filter through ash-free filter paper, and wash with hot water until the combined filtrate and washings measure to about 60 cubic centimeters. Return the filter and contents to the platinum dish, carefully ignite, cool, and weigh. Compute percentages of water-insoluble ash and water-soluble ash. Number 10. Alkalinity of the soluble ash. Official. Cool the filtrate from 9 and titrate with N/10 hydrochloric acid using methyl orange as an indicator. Express the alkalinity in terms of the number of cubic centimeters of N/10 acid per 1 gram of the sample. Number 11. Soluble phosphoric acid in the ash. Official. Acidify the solution of soluble ash obtained in 9 with dilute nitric acid and determine phosphoric acid, P2O5. For percentages up to 5, use an aliquot corresponding to 0.4 gram of substance. For percentages between 5 and 20, use an aliquot corresponding to 0.2 gram of substance, and for percentages above 20, use an aliquot corresponding to 0.1 gram of substance. Dilute to 75 to 100 cubic centimeters, heat in a water bath to 60 to 65 degrees centigrade, and for percentages below 5, add 20 to 25 cubic centimeters of freshly filtered molybdate solution. For percentages between 5 and 20, add 30 to 35 cubic centimeters of molybdate solution. For percentages greater than 20, add sufficient molybdate solution to ensure complete precipitation. Stir, let stand in the bath for about 15 minutes, filter at once, wash once or twice with water by decantation using 25 to 30 cubic centimeters each time, agitate the precipitate thoroughly and allow to settle. Transfer to the filter and wash with cold water until the filtrate from 2 fillings of the filter yields a pink color upon the addition of phenolphthalein and 1 drop of the standard alkali. Transfer the precipitate and filter to the beaker or precipitating vessel. Dissolve the precipitate in a small excess of the standard alkali. Add a few drops of phenolphthalein solution and titrate with the standard acid. Number 12. Insoluble phosphoric acid in the ash. Official. Determine phosphoric acid, P2O5, in the insoluble ash by the foregoing method. 13. Chlorides. Official. Moisten 5 grams of the substance in a platinum dish with 20 cubic centimeters of a 5% solution of sodium carbonate, evaporate to dryness and ignite as thoroughly as possible at a temperature not exceeding dull redness. Extract with hot water, filter, and wash. Return the residue to the platinum dish and ignite to an ash. Dissolve in nitric acid and add this solution to the water extract. Add a known volume of N/10 silver nitrate in slight excess to the combined solutions. Stir well, filter, and wash the silver chloride precipitate thoroughly. To the filtrate and washings, add 5 cubic centimeters of a saturated solution of ferric alum and a few cubic centimeters of nitric acid. Titrate the excess silver with N/10 ammonium or potassium thiocyanate until a permanent light brown color appears. Calculate the amount of chlorine. 14. Caffeine. The Fendler and Stuber method. Tentative. Pulverize the coffee to pass without residue through a sieve having circular openings 1 mm in diameter. Treat a 10-gram sample with 10 grams of 10% ammonium hydroxide and 200 grams of chloroform in a glass stoppered bottle and shake continuously by machine or hand for 1/2 hour. Pour the entire contents of the bottle on a 12.5 centimeter folded filter, covering with a watch glass. Weigh 150 grams of the filtrate into a 250 cubic centimeter flask and evaporate on the steam bath, removing the last chloroform with a blast of air. Digest the residue with 80 cubic centimeters of hot water for 10 minutes on a steam bath with frequent shaking and let cool. Treat the solution with 20 cubic centimeters for roasted coffee or 10 cubic centimeters for unroasted coffee of 1% potassium permanganate and let stand for 15 minutes at room temperature. Add 2 cubic centimeters of 3% hydrogen peroxide containing 1 cubic centimeter of glacial acetic acid in 100 cubic centimeters. If the liquid is still red or reddish, add hydrogen peroxide 1 cubic centimeter at a time until the excess of potassium permanganate is destroyed. Place the flask on the steam bath for 15 minutes, adding hydrogen peroxide in 0.5 cubic centimeter portions until the liquid becomes no lighter in color. Cool and filter into separatory funnel, washing with cold water. Extract 4 times with 25 cubic centimeters of chloroform. Evaporate the chloroform extract from a weighed flask with aid of an air blast and dry at 100 degrees centigrade to constant weight. 1/2 hour is usually sufficient. Weigh the residue as caffeine and calculate on 7.5 grams of coffee. Test the purity of the residue by determining nitrogen and multiplying by 3.464 to obtain caffeine. 15. Caffeine. Power chestnut method. Official. Moisten 10 grams of the finely powdered sample with alcohol, transfer to a soxhlet or similar extraction apparatus, and extract with alcohol for 8 hours. Care should be exercised to assure complete extraction. Transfer the extract with the aid of hot water to a porcelain dish containing 10 grams of heavy magnesium oxide in suspension in 100 cubic centimeters of water. This reagent should meet the USP requirements. Evaporate slowly on the steam bath with frequent stirring to a dry, powdery mass. Rub the residue with a pestle into a paste with boiling water. Transfer with hot water to a smooth filter, cleaning the dish with a rubber-tipped glass rod. Collect the filtrate into a liter flask marked at 250 cubic centimeters and wash with boiling water until the filtrate reaches the mark. Add 10 cubic centimeters of 10% sulfuric acid and boil gently for 30 minutes with a funnel in the neck of the flask. Cool and filter through a moistened double paper into a separatory funnel and wash with small portions of 0.5% sulfuric acid. Extract with 6 successive 25 cubic centimeter portions of chloroform. Wash the combined chloroform extracts in a separatory funnel with 5 cubic centimeters of 1% potassium hydroxide solution. Filter the chloroform into an Erlenmeyer flask. Wash the potassium hydroxide with 2 portions of chloroform of 10 cubic centimeters each, adding them to the flask together with the chloroform washings of the filter paper. Evaporate or distill on the steam bath to a small volume, 10 to 15 cubic centimeters, transfer with chloroform to a tared beaker, evaporate carefully, dry for 30 minutes in a water oven, and weigh. The purity of the residue can be tested by determining nitrogen and multiplying by the factor 3.464. 16. Crude fiber. Official. Prepare solutions of sulfuric acid and sodium hydroxide of exactly 1.25% strength determined by titration. Extract a quantity of the substance representing about 2 grams of the dry material with ordinary ether, or use residue from the determination of the ether extract. To this residue, in a 500 cubic centimeter flask, add 200 cubic centimeters of boiling 1.25% sulfuric acid. Connect the flask with a reflux condenser, the tube of which passes only a short distance beyond the rubber stopper into the flask, or simply cover a tall conical flask, which is well suited for this determination, with a watch glass or short-stemmed funnel. Boil at once and continue boiling gently for 30 minutes. A blast of air conducted into the flask may serve to reduce the frothing of the liquid. Filter through linen and wash with boiling water until the washings are no longer acid. Rinse the substance back into the flask with 200 cubic centimeters of the boiling 1.25% solution of sodium hydroxide, free, or nearly so, of sodium carbonate. Boil at once and continue boiling gently for 30 minutes in the same manner as directed above for the treatment with acid. Filter at once rapidly, wash with boiling water until the washings are neutral. The last filtration may be performed upon a Gooch crucible, a linen filter, or a tared filter paper. If a linen filter is used, rinse the crude fiber after washing is completed into a flat-bottomed platinum dish by means of a jet of water. Evaporate to dryness on a steam bath, dry to constant weight at 110 degrees centigrade, weigh, incinerate completely, and weigh again. The loss in weight is considered to be crude fiber. If a tared filter paper is used, weigh in a weighing bottle. In any case, the crude fiber after drying to constant weight at 110 degrees centigrade must be incinerated and the amount of the ash deducted from the original weight. 17. Starch. Tentative. Extract 5 grams of the finely pulverized sample on a hardened filter with 5 successive portions, 10 cubic centimeters each, of ether. Wash with small portions of 95% alcohol by volume until a total of 200 cubic centimeters have passed through. Place the residue in a beaker with 50 cubic centimeters of water. Immerse the beaker in boiling water and stir constantly for 15 minutes or until all the starch is gelatinized. Cool to 55 degrees centigrade. Add 20 cubic centimeters of malt extract and maintain at this temperature for an hour or until the residue, treated with iodine, shows no blue color upon microscopic examination. Cool, make up directly to 250 cubic centimeters and filter. Place 200 cubic centimeters of the filtrate in a flask with 20 cubic centimeters of hydrochloric acid, specific gravity 1.125. Connect with a reflux condenser and heat in a boiling water bath for 2.5 hours. Cool, nearly neutralize with sodium hydroxide solution, and make up to 500 cubic centimeters. Mix the solution well, pour through a dry filter and determine the dextrose in an aliquot. Conduct a blank determination upon the same volume of the malt extract as used upon the sample, and correct the weight of reduced copper accordingly. The weight of the dextrose obtained multiplied by 0.9 gives the weight of starch. 18. Sugars. Tentative. See original Association of Official Agricultural Chemists, September 1920. 19. Petroleum ether extract, official. Dry 2 grams of coffee at 100 degrees centigrade, Extract with petroleum ether, boiling point 35 to 50 degrees centigrade, for 16 hours. Evaporate the solvent. Dry the residue at 100 degrees centigrade. Cool and weigh. 20. Total acidity. Tentative. Treat 10 grams of the sample, prepared as directed under 4, with 75 cubic centimeters of 80% alcohol by volume in an Erlenmeyer flask, stopper, and allow to stand 16 hours, shaking occasionally. Filter and transfer an aliquot of the filtrate, 25 cubic centimeters in the case of green coffee, 10 cubic centimeters in the case of roasted coffee, to a beaker. Dilute to about 100 cubic centimeters with water and titrate with N/10 alkali using phenolphthalein as an indicator. Express the result as the number of cubic centimeters of N/10 alkali required to neutralize the acidity of 100 grams of the sample. 21. Volatile acidity. Tentative. Into a volatile acid apparatus introduce a few glass beads, and over these place 20 grams of the unground sample. Add 100 cubic centimeters of recently boiled water to the sample. Place a sufficient quantity of recently boiled water in the outer flask and distill until the distillate is no longer acid to litmus paper. Usually, 100 cubic centimeters of distillate will be collected. Titrate the distillate with N/10 alkali using phenolphthalein as an indicator. Express the result as a number of cubic centimeters of N/10 alkali required to neutralize the acidity of 100 grams of the sample. Unofficial methods. 22. Protein. Determine nitrogen in 3 grams of the sample by the Kjeldahl or Gunning method. This gives the total nitrogen due to both the proteids and the caffeine. To obtain the protein nitrogen, subtract from the total nitrogen the nitrogen due to caffeine, obtained by direct determination on the separated caffeine or by calculation. Caffeine divided by 3.464 gives nitrogen. Multiply by 6.25 to obtain the amount of protein. 23. 10% extract. McGill method. Weigh into a tared flask the equivalent of 10 grains of the dried substance. Add water until the contents of the flask weigh 110 grams. Connect with a reflux condenser and heat, beginning the boiling in 10 to 15 minutes. Boil for 1 hour, cool for 15 minutes, weigh again, making up any loss by the addition of water, filter, and take the specific gravity of the filtrate at 15 degrees centigrade. According to McGill, a 10% extract of pure coffee has a specific gravity of 1.00986 at 15 degrees centigrade, and under the same treatment, chicory gives an extract with a specific gravity of 1.02821. In mixtures of coffee and chicory, the approximate percentage of chicory may be calculated by the following formula. 1.0281 specific gravity. Percent of chicory equals 100 over 0.01835. The index of refraction of the above solution may be taken with the Zeiss immersion refractometer or with the Aber refractometer. With a 10% coffee extract, ND 20 degrees equals 1.3377. With a 10% chicory extract, ND 20 degrees equals 1.3448. Determinations of the solids, ash, sugar, nitrogen, etc., may be made in the 10% extract if desired. 24. Cafetanic acid. Krug's method. Treat 2 grains of the coffee with 10 cubic centimeters of water and digest for 36 hours. Add 25 cubic centimeters of 90% alcohol and digest 24 hours more. Filter and wash with 90% alcohol. The filtrate contains tannin, caffeine, color, and fat. Heat the filtrate to the boiling point and add a saturated solution of lead acetate. If this is carefully done, a cafetanate of lead will be precipitated containing 49% of lead. As soon as the precipitate has become flocculent, collect on a tared filter, Wash with 90% alcohol until free from lead. Wash with ether. Dry and weigh. The precipitate multiplied by 0.51597 gives the weight of the cafetanic acid. End of section 22.